you kind of work things out over the next week or so on your own. And we should have certainly Tuesday, if not both Monday and Tuesday, to practice and look at some things and have a chance to kind of recap what we've done. So feel free to kind of just start working on any additional related rates problems that are in there. There's, like I said, like 5 or 6 pages of them, and I've got lots more. I don't know if you noticed, but like our last guided notes ended on page like 270, and the one that you're going to get from me today starts on 293. So that's 25 plus pages of additional problems if you think you need them. Okay, but we're going to put a temporary hold on that tab, and I'm going to give you this one. You're going to see how super short this one is, because we're only going to do this for a couple days. We will have actually something I'm going to supplement this with. There's one idea that hopefully we can get to. We'll see if it works out. That just isn't in the guided notes that they created. It's something that I'll probably just add. So you can put your related rates stuff away and focus only on this one right here. Okay, second derivative ideas. I don't know how much we've talked about second derivative stuff on much of a deep enough level to make it worthwhile. So we will put your name at the top if you think you need to. Here we are on 293. Okay, like I said, I got to pick up the pace a little bit because we lost about 10 minutes. So analytical and graphical connections between a function, its derivative, and its second derivative. And you can see in the title there how we're going to write it f double prime. Okay, oh, thanks. Okay. And so what I want to do, I think this is a good one to kind of start focusing on first is this one right here. In order to start understanding what the second derivative can do, I want to make sure that we kind of can, let me rephrase, hold on. What the second derivative can do for us to understand the function better is I want to make sure that we make a connection from the second derivative back to the first. And then kind of work our way back that way. Instead of taking kind of a 2 degrees of separation kind of leap from the second derivative all the way back, let's make just kind of one leap at a time. And I think the easiest way to do that, to try to make a connection between this graph right here, whatever this f of x is, to its second derivative, is to have a first derivative conversation first, okay? And so what I'm going to do here is I'm just going to kind of mark this up. I think the best thing that you can do is just watch and make sense of it, okay? Write down stuff if you think you need to, but you'll see on the next few pages, a lot of the ideas that we're going to discuss and kind of grapple with will be formalized in the next couple of pages. So I think you'll have a chance to write stuff down. So what I'm going to do is I'm going to draw some tangent lines along the way. And we are going to have a discussion about kind of what happens as we move from one side to the other. As we move from left to right, what is happening at some of these spots? And I'm just alternating colors to make it a little bit easier for us to see what's happening. And I'm just going left to right, and I just want to kind of look at, okay, what is the derivative doing from one side to the next? Okay, because hopefully what you start to see, that was a terrible one. What you hopefully, that didn't change colors. What you hopefully, third time's a charm, there we go. What you start to see maybe is how the second derivative connects back to the first. And what I think would be a helpful exercise would be to just estimate these slopes from left to right. What do you think? Take a look at that graph. What do you think the slope of that is right there? I don't care how close we are, just a decent halfway, decent guess. 4? Cool. And what about that one? If this is 4, what's that? 3. Okay. If this is 3, what's the blue one? 2. Okay. What about the red one? 1. What about the blue one? 0. Okay. So what is happening to the derivative as we move from left to right? Get smaller. Okay, cool. Now let's hop over that relative max right there What's that slope? What do you think of that red one? -1. Okay, then this one?
-2.
Okay. Is it still decreasing?
Yeah.
Okay. So what we saw with the first derivative is that the function changes from increasing to decreasing at a relative max, or at a relative max. The second derivative doesn't make that change at that spot. It's only the first derivative that goes from positive to negative at a relative max, right? And so when we think about what the second derivative is going to do, hopefully we're starting to make a little bit of connections. The first derivative describes what the function is doing, whether it's increasing or decreasing. What the second derivative is going to do is describe how the first derivative is changing. Is the first derivative increasing, or like this, is the first derivative decreasing? Okay, and that does not tell me necessarily about what's happening with the function just yet. We'll get to it here in a second, right? It goes increasing to decreasing for the first derivative, but the whole way that function is the derivatives are decreasing. Okay, but what happens here? 1, 0, -1, -2. Kind of -2-y, maybe, something like that. Okay, what about the blue? Now back to -1. 0. What do you think?
1, 2, 3, 4.
1, 2, 3, 4. Good enough for me. Maybe it goes 2, 4, 6, 8, whatever. Right? But it's getting bigger. Okay? So it goes from positive, so first derivative, positive to negative to positive, which makes a lot of sense, right? Increasing to decreasing to increasing. But think about what the second derivative can tell us about the first derivative. The second derivative should describe how the first derivative is changing. It is decreasing till about there, right? Let me put a little point like right here. And now it's increasing. Because it goes -2, -1, 0, 1, 2, 3, 4. The first derivative is increasing in that whole section. Okay, so we've got like a section over, I'm just going to kind of redraw it over here. We've got like this section right here. So right about like there. All right, here's that point right there. And then we've got this section right there. And the second derivative is kind of changing along the way. Because second derivative describes how the first derivative is changing. And so here's what we know so far, right? If the function is increasing, what do we know? What's the first derivative? The function is increasing. What do we know about the first derivative just kind of in general? It's positive. Gonna be for sure. Okay. So let me ask you this. What if f prime is increasing? Right, that blue section over there.
Would f double prime be positive?
There you go. Okay. And so what we can do is start to make connections from the second derivative back to the first. And say, oh, if the second derivative is positive, oh, then the first derivative must have been increasing along the way. And the only way that that can happen is when things look like this. Right? It doesn't have to have that like full parabola version. I can take a section of that, and the second derivative is going to be positive. Okay. This whole thing right here, this section where the graph looks like that blue section, that whole space is where the second derivative is positive, right? Of course, the first derivative can change from negative to positive or positive to negative, kind of depending on what things look like. But the second derivative in that whole space is going to be positive. Okay, let's do another one. What if f of x is decreasing? What do we know about the first derivative? Negative, okay. And so what if f prime is decreasing? What do we know about the second derivative? It's negative. Okay, and that's this section right here. okay? And we can give those names because of the way that they look. And I'm telling you, that's the only way that these can be drawn. That red section, or part of the red section. It doesn't have to be the whole thing. And then the blue section. So what the second derivative does is it describes that shape, okay? Yeah, sure, it can get us back to the first derivative being decreasing or increasing, whatever. But I don't really care much about the first derivative. Like, give me some details about the second derivative. I want to know what the functions do. Give me back to the original, okay? And so the description of the graph that we can get from the second derivative has a name, okay? And it's called concavity. Okay? The graph in sections, right, within intervals, can have different types of concavity, okay? Maybe, like this blue section, it has that kind of like upward facing parabola look to it, right? We call that concave up because it opens upwards. Okay, that's that whole blue section over there. What do you think about the red section? If the blue section is concave up, what do you think the red section is kind of that downward facing parabola? Concave down. That's it. Concave down. Okay, this happens when the second derivative is negative. This happens right here. Sorry, I'm out of space. Where the second derivative f double prime is positive. So, what is that then? Whole red section concave down. I don't care what spot you pick, plug that number into the second derivative, it's going to be negative something. Same thing with the blue, but just in the positive version. So what do you think is happening at that black point where concavity changes? What do you think the value of the second derivative is going to be at the point where it's not concave down anymore, but it's not concave up yet? 0. Okay, this is called an inflection point, which you already know. But now we can formalize it. I'm going to come down here. I'm going to give this a name. Okay, where concavity changes. Okay, an inflection point is where concavity changes from down to up or up to down. Now, is that black point right there a relative min or a relative max for the function itself? No, and that's okay. It's not going to be. Right, I know we think a lot about like first derivative being equal to 0. That's where the tangent line is 0. And oh, we could have a relative min, we could have a relative max. Or hey, maybe we have neither, right? There's an inflection point right there because it goes from concave down. That's not the whole parabola, but it is half of it, okay? That should be in red, actually. Concave down to concave up, okay? And so that's a little hard to see when it's not the whole parabola, right? And I think about like putting a drop of water and letting it like drop onto it and kind of like comparing what would happen to that droplet of water. Like drop that water droplet into the blue section over there, the one on the right. Is it going to pool at the bottom or roll off the top? It's going to pool in the bottom. That's concave up. I have a bowl. I have a place to put it. Okay. What about the red section? Is it going to pool somewhere or is it going to roll off? That's the difference. Okay. And so when I think about doing that here, I just kind of like pick the middle of the section, right? If there was another half, it would pool in it, okay? Versus putting it here, it's going to roll off that side. And that's a big part of what the second derivative can do, is tell us intervals of concavity versus intervals of increasing and decreasing with the first derivative. This is intervals of concave up versus concave down, okay? And of course, what's the point that's going to break those apart? Inflection points. Just like critical numbers, we're going to break things apart for us, increasing versus decreasing potentially. So we can find mins and maxes. Same thing here. We can find inflection points and kind of create some intervals of concavity. And that's all we're going to do today is worry about, okay, can I find an inflection point? Can I figure out where this graph changes something? First derivative was about changing increasing to decreasing. This is about changing from concave down to concave up or vice versa. Okay, basic beginnings of second derivative. Cool with that? Okay, now let's back up a little bit and actually read and talk a little bit about the difference between these two graphs. Okay, and we've mentioned these ideas before, but I just wanted to make sure that we actually say them a little bit more officially, I guess. Okay, now you know how to take derivatives of everything. You got it all. Okay, we just have to kind of tweak our understanding just a little bit. And we've had this conversation a little bit from time to time, but not a whole lot about, like what is happening as we approach a relative max or a relative min with the value of the first derivative, right? It goes, like you said, like 5, 4, 3, 2, 1, 0. -1, -2, -3, -2, -1, 0, 1, 2, 3, right? It has kind of a flow to it, like a natural, nice, right? I'm starting positive, but I start to slow down, right? I'm getting closer and closer to 0, and then, oh, look, I hit 0. And now I'm like a little bit past 0. And then, I start to get more negative. Oh, but eventually I better slow down. I'm going to get like closer and closer to 0. And then, oh, look, I hit 0. What is happening as we go from left to right? 5, 4, 3, 2, 1, 0. -3, -2, -1, 0. Are they both approaching the same derivative value? They're both approaching 0. So the limit of the derivatives is 0 from both sides. So the derivative exists at that point. Does that make sense? Right? The whole idea with like limits is if I want a limit to exist, I better approach the same value from both sides. Same thing here, right? -3, -2, -1, 0. 3, 2, 1, 0. Both approaching the same value. So the derivative exists at that spot, which makes a whole lot of sense. What about the derivative approaching this spot right here, which is called a cusp? Me too. Okay. And you can kind of imagine like bouncing a ball off the ground. What is happening? Well, think about the value of the derivative, like -1, -2, -3, -5, -10, -100, -1,000, -1,000,000. We're getting super steep as we approach. What are we headed towards? -1, -2, -10, -100, -1,000, -1,000,000. Headed towards negative infinity. Okay, now let's approach the same point from this side. +1, +2, +3, +5, +10, +100, +1,000, +1,000,000. What derivative value are we approaching from the right? 1, 2, 5, 10, 100, 1,000, 1,000,000. Are we headed towards the same spot?
No.
So what do you think? Is the value right here, which is a point, it's defined, right? Plug in -1, I get 2. The point's defined is the derivative, and that's okay. Okay, we can have relative mins and maxes at points where the function is defined. Of course, we need a point to do it, but the derivative is not. Okay, the derivative is undefined. Because when you think about what values x has right here of maxes and mins, yeah, like 0 and 2, right? We have a minimum at 2 comma whatever, and we have a max at 0 comma whatever. And yeah, if I look at this graph here on the right, absolutely, x equals, I don't really need the set notation, I'm just going to write it anyway, just for consistency, right? -1, there's a relative in there. It's just a big difference between what we see with our derivative process with g of x compared to f of x. All right, g of x, basic power rule stuff, 3x squared minus 6x, sweet. Something quadratic, I get 2 answers, there they are, 0 and 2. But think about finding the derivative of f of x. You know, it's got a power, so we'll that's the big thing happening. So we'll drop the 2/3 in front. We'll chain rule, leave the inside the same, decrease the power by 1 though. We end up with this negative 1/3 as the exponent for this x plus 1. Negative 1/3 is going to move down to the bottom of this fraction. If I plug in negative 1, we're going to get something over 0, which of course is undefined. And that's okay. We can still be confident enough in the work that we've done to say, well, you know, g prime of x is going to be equal to 0 at all of those spots for g of x where we're going to find the min and the max. Why? Because the limit of the derivative from the left and from the right is the same. Okay, but big difference over here, okay? This is going to be undefined. Now that's not second derivative stuff, that's first derivative stuff. But I think the second derivative will eventually aid us a little bit in saying, all right, how do I deal with mins and maxes? Of course, I need the first derivative to help me find them. But how can I verify whether it's a minimum or whether it's a maximum at some of these points that exist? If the derivative exists at that spot and it's equal to 0, okay, that makes it a little bit easier because what we did, we test on the left, we test on the right. Did it go positive, 0, negative, or negative, 0, positive, right? We did that first derivative test. How can the second derivative help us out? And we'll get to that tomorrow. Right, we're going to skip a couple things here because they say, like, go ahead, do it, right? Perform a sign analysis. And that's just what we did. Negative, getting bigger and bigger and bigger. Positive, getting bigger and bigger and bigger. And so that kind of lays down the rules for us. Go ahead and turn the page. Yeah, I'm going to go a little bit quicker today because the concepts aren't super tricky. And before I start working through this stuff, are we good with picturing concavity? Concave up, parabola opens up. Concave down, parabola opens down. But it could be just like half of it. It doesn't have to be the whole thing, right? It could be either half and it's still concave up. Could be either half and it's still concave down in that whole section, okay? And so what the last page did, and here they are formalizing it, right? For a long time, we just dealt with polynomials early and often, and we just found where the first derivative was 0. Now we can find spots where the function exists, but it's just not differentiable at that spot, meaning the derivative is undefined, okay? And the most common one that you'll ever run into, okay, is that cusp, okay, where it kind of like hits this sharp point. Polynomials we love, they're smooth and rounded and easy and all continuous everywhere. Right, things that have that 2/3 power, 4/3 power, 5/3 power, we're going to see that thing. And so it doesn't exclude the relative min or max possibility from that spot. Okay, and so when we talk about defining critical numbers, it's where the first derivative is equal to 0 or where it's undefined. Okay, and we want to check all those spots. And hopefully we can find an easier way to figure out whether it's a minimum or a maximum without having to go through all that process to find, okay, like interval stop, and kind of doing that sign analysis, that first derivative test on either side. Eventually, by tomorrow, okay? Now, I don't think we need to fill out this table again, right? If it's 0 undefined, could be a min or a max. If it's greater than 0, it's increasing. If it's less than 0, it's decreasing, right? We can do all of those kind of things. I think, correct me if I'm wrong, we kind of understand first derivative, increasing, decreasing, positive, negative, okay? Okay, bottom of this page. This is kind of what I was alluding to, right? The first derivative can give us increasing intervals, decreasing intervals, figure out whether we have relative maximum, minimum, whatever we need to find. Okay, in a very similar way, the second derivative tells the same story about the first, like the first tells a story about the function itself. And what we figured out is we can figure out concave up versus concave down and inflection points where it's zero. Okay? And that's what I want to try to do here. Go ahead, flip the page one more time. With the function that they just listed on the page before, so I'm just going to write it down again. F of x, and if you want to write it down so you don't have to keep peeking back and forth. I think it was x cubed minus 3x squared. Is that it? Cool. There we go. So there's our function. And just to get us used to second derivative stuff, we're going to go through a very similar process that we do with the first derivative. And let's find critical numbers, and let's use those to break the function into intervals where it's going to be increasing or decreasing. Now we're going to find inflection points and break the function into concave up versus concave down. Okay. Once we do that, at least once, maybe twice, then tomorrow we can kind of use that a little bit. Okay, so, oh, G, sorry, not F. G. Okay, how do you think we're going to do it, though? Like, here's a function. They give us this polynomial. How are we going to find a function for the second derivative? How are we going to find the derivative of the derivative of g of x? That's all a second derivative is. The derivative of the derivative. Yeah?
Yep, on the first derivative first.
And then
Take the derivative.
do it again. That's it. Okay, the second derivative, the only way to do it, find the first derivative, and then find the derivative of that. Let's do it. G prime. Here at the second half of chapter 4, hopefully they pick relatively nice functions for us to start in. Or, you know what, they might even just give us the first derivative. They're going to say, like, here's h prime of x, find h double prime. You only have to do it once, so you want to kind of watch out what they're giving us. But if they give us the function, all right, cool, a little power rule right there, right? 3x squared minus 6x. Keeping it nice for us. If we wanted to find critical numbers, right, potential extremum, we'd set that equal to 0 and solve it. But that's not what we want. We want to try to find inflection points. Let's find g double prime. Okay, 6x minus 6. Take the derivative again. That's Newton's notation, right, with the prime and the double prime. I will show you Leibniz's tomorrow, just so you can see that. But there we go. Let's figure out, so look at the question, right? Find g double prime, done. Perform a sign analysis, meaning like the test that we did, interval stop, interval stop, interval stop, interval stop, to figure out where things are concave up and where things are concave down. And that second question is really hitting the nail on the head. At what values of x does the sign change? We're looking for inflection points. And so what do you think we do here with this second derivative if we want to find, however, and this is linear, so just the one inflection point?
Oh, so where x is 0.
Set it equal to 0. Just like critical values are going to be found where we set the first derivative equal to 0. We saw on a couple pages before when we were looking through it, let's actually set this thing equal to 0 and solve. Whatever we get, we should be able to find whatever our inflection point is. So what, add 6 divided by 6, 1? That is your inflection point. And what should happen with this point, this x equals 1, is it should break the function into two pieces, right? One inflection point, look at me for a second, right? Two intervals on either side, right? Kind of like we did, right? 2 and 3 and 3 and 4. What that should do is allow us to break things apart and say, okay, let me check my intervals. It used to be critical numbers. Let me check my intervals and my inflection points. We'll look at the sign of f double prime, and that should help us describe the behavior. And right now, we only have 3 pieces. Interval stop, interval stop, interval stop, interval stop, as many as you need, right? Let's go from negative infinity to 1. We'll stop at 1, and then we'll go from 1 to infinity. Do you remember this from first derivative stuff, like chapter, like maybe chapter 3, like early chapter 3 or like late chapter 2? All right, we just did it with the first derivative to help us find mins and maxes. and intervals of increasing, decreasing. Now what we can do is we can figure out where our inflection points are, where the sine of f of x, here's an easy one, right, where it's 0, f double prime. I know that at x equals 1, it's going to be 0, which means I have an inflection point. I'm just going to put I, inflection point. And we just want to figure out, okay, to the left of that, is it concave up or concave down? Now, I could go from increasing to decreasing, and there could be a min or a max over there. Who knows? Second derivative doesn't help us with that just yet. We just want to figure out where this thing is going up or going down in terms of its concavity. So what do you think? We want to do this little quick sign analysis for f double prime, and we've got all the numbers between negative infinity and 1 to choose from. What should we pick? Negative 2, 0, negative 1,000,000. Who cares? Doesn't matter which one. I'm going to pick 0 because that's real nice. Any chance I can get to plug in 0 works for me. Where am I putting it? I'm putting it right here. Plug in 0, we get negative 6. So the sign is the only thing I care about. Again, it's negative. So what do you think we could say about the behavior of the function in that whole interval where the second derivative is negative? Concave down. And sections that are concave down look like this. Something like that. Something. Okay. Now we can plug in a number bigger than 1, less than infinity. Pick a number. Yay, sounds good. We're going to get 6. So what do you think about the behavior of the function? Concave up. Concave up sections look like that. What's in between an inflection point? Look back a page or two. Is that the exact graph that we're looking at? It's the first graph. It's the same function. That's exactly what that looked like. Now, we don't know exactly where it's going to take a turn, mins, maxes. But I know where the inflection point is, and I know that it's concave up and concave down. I know what things are going to look like, at least a little bit. Now, does the second derivative tell me everything? No. Just like the first derivative didn't tell me everything, hey, at least I know something. Okay, at least I know something. It's really about putting the two together that's going to make this thing worthwhile. Okay. We've got 5 minutes, right? Should we fill out that little table there? Let's do it. I like it. Now, I think you're going to feel like this makes a whole lot of sense if you remember how the second derivative, like what the second derivative can tell us about concavity. So, what do you think? If the second derivative is 0, or it's undefined at some x equals a, what is happening right there at that point? An inflection point. F of x has an inflection point, and this is at x equals a, right? It's actually at a point itself. And just like with critical numbers, it only tells us about that one spot, the one thing. And I don't really know whether it's going from concave up to concave down or concave down to concave up, but something's going to happen there. Okay, what if the second derivative is greater than 0? Got to be concave up. And f of x is concave up. And if you need to do this, this might be a little helpful little picture to draw. Right? Draw yourself a little upward-facing parabola, a nice little visual to go with it. So you can remember. And again, it could be any part of that. It doesn't have to be the whole thing. Any section of that graph is concave up. And look, it goes from decreasing to 0 to increasing. Guaranteed, because it's got to be concave up. Okay, what if our second derivative is negative? Yep, concave down. Down, which looks like that. Okay. You can see they kind of lump these two together. What if we change the second derivative's sign from positive to negative or from negative to positive? What's the only way to do that? got to go through an inflection point to do it, right? Kind of like when we went from increasing to decreasing, we had to go through an extrema or vice versa. Absolute same thing, right? When we see that change happen, if we were to do that sign analysis, right, and not even know where an inflection point is, if we see it change, we know we had to go through an inflection point. Okay, now second period was able to do f of x down there at the bottom. Okay, we've got like 2 minutes. See if you can at least get yourself a second derivative for us to start with tomorrow. Because what you can see is that they're saying, okay, here's a function, find the x values where you have a point of inflection. And then we'll figure out concave up and concave down intervals. Only way to do the second derivative is to find the first and then do it again. And if you've got the last 30 seconds, you can start setting up your analysis, or even at least find your inflection point. That's how we'll start. Okay, we will set the second derivative equal to 0. We'll solve that. It's quadratic, so we'll probably get 2 different ones. That's cool. 2 inflection points, so 3 intervals of concavity. And that'll start. Have a great day. I will see you tomorrow. Thanks, everybody.
You add a point for everything.
Thank you.
You're welcome. Have a good one.
When you don't have that